Hello, everyone, and welcome to this week's edition of the Cassandra Community Webinar Series. My name is Paige Ruman, and I will be hosting today's webinar. I'll be available via the chat box throughout the presentation if you have any technical difficulties. A few housekeeping items before we get started. Please submit all of your questions through the Q&A box, and we will get to them at the end of the presentation. We will also be recording the webinar, which will be available along with the slides on the DataStax website tomorrow. And finally, DataStax will be hosting this year's Apache Cassandra Summit at Fort Mason. It's a two-day event for the Cassandra community filled with an all-star lineup of speakers and sessions with great food and cool giveaways. If you're interested in attending, please use the code SFSummit25 to receive 25% off of regular price tickets. Today we'll have our very own Cassandra guru, Patrick McFadin, presenting the first of this three-part data model series. Prior to working for DataStax, Patrick was the chief architect at Hobsons, an education services company. He was responsible for ensuring product availability and scaling for all higher education products. Prior to this position, he was the director of engineering at Hobsons, which he came to after they acquired his company, Linked 11 Systems, a software services company. While at Linked 11 Systems, he built the first widely popular CRM system for universities, Connect. He has a BS in computer engineering from Cal Poly and holds the distinction of being the only recipient of a medal for hacking while serving the U.S. Navy. So without further ado, Patrick, take it away.
And let me unmute my mic. All right, so I got to share my screen now. Hold on here. You're going to hand me the ball there.
Yep, doing it now.
All right. Sorry. This is what we do all the time, right? Okay, so thank you very much, Paige. Let me get my application shared here. So, all right, there we go. So today I'm going to talk about data modeling. And so I'm hoping there's a lot of people that I've talked to on the phone here today. I seem to meet a lot of Cassandra people, people interested in getting into Cassandra, from bridging over from all different places. But if I've never talked to you before or you're new to this topic, welcome. I'm really interested in trying to get people updated into what's going on with Cassandra if they're coming from a relational world. So this has been a really hot topic for me, just the whole data modeling thing, because that's really, I feel like, a question I hear all the time is, well, I knew how to do data modeling before when I did relational databases in Oracle and MySQL, but how do I even translate any of that? How do I get any of that into Cassandra? And so this is what this is about. So this is actually the first of three presentations I'm going to do, so a three-part series. So this is the beginning. This is more of like, here's the start. And then at the end of it, I'll have a slide show you the next couple that I have. But really, this should be treated as kind of a three-part. So this will get you started. The next one's going to be more advanced. And then the third one is going to be kind of a wrap-up. So let's start this thing out with that divide. So I really wanted to put something up there that pointed out what I'm talking about. So bridging the divide in what I'm using here is all about, well, you know, a lot of education has gone around data modeling and relational data stores. And I took a college class in relational algebra and relational calculus. That was what we did. And, you know, thank you, Edgar Cod, for giving us that wonderful thing. But you just learned how to, you know, create normal data. And I have some slides on what we did there. But now I really feel like, this has probably been years past. I'm kind of late to saying this, but the end of relational everything is over. And, you know, I have my picture of vanilla ice cream cone here. But that was really what it was. Is we need a database. Oh, well, all right, do you want to use, which relational technology do you want to use? Do you want a SQL Server, MySQL? How about Oracle? Sometimes it always turned out to just be Oracle. Even Informix or something like that. But that was always the answer. Okay, well, you got to store data. You got to put it in there. And if you're unfortunate enough to live in a place that loves mainframes, so you could do that too. But that wasn't really relational anyway. So this whole idea of polyglot persistence is really interesting. Now, polyglot persistence is about, like the picture shows, with multiple flavors. So if you get a chance, check out this Martin Fowler link. It's pretty interesting because I think it'll actually resonate pretty well with you. We're not putting data in one place anymore. I remember, you know, when we brought Memcache into our environment, and we didn't really consider that NoSQL, but that was kind of the gateway drug. You understood, oh, wait a minute, we could be storing data in different places. And it's okay because we want to put our data in a place that makes sense, not so much we want to put our data in a place that we have just one of. And so it's changing the way we build applications because we have different questions, we have different answers. And so this polyglot persistence is real. You can look in your, probably right now you can look in your infrastructure and say, okay, yeah, we got some of that. So Cassandra fits in there nicely because with relational technologies or something like Cassandra, you know, those are two different places and two very different ways to store data. Now with DataStax, of course, we've kind of created our own little vanilla or different flavors of ice cream with adding Solar and Hadoop and also with Cassandra. So we're embracing that idea in one product offering, but there's a lot more out there as well. So I was an Oracle DBA for years and years and years because, let's just face it, it was hard to not find a job doing that. And I was a relational database developer. I made a lot of money doing that. It was good times, but I always had the same problems. And this is slightly trolly, but it's kind of true because when I think about, okay, now what are the easy and the hard, and this is, so taking this from, here's me, Patrick McFadin, guy who's big-time relational dude, and I used to argue a lot that relational was going to end everything, but you get into these arguments and then there's these questions that come up that don't exactly have good answers. So this was me, and I'm looking at Cassandra versus my relational database, and this is what I see. Okay, single point of failure. All right, yes, that's kind of that's not so easy with a relational database. Sure, you can get rack. Sure, you can use clustering, but that's, you know, you got to find somebody who knows how to do it, and you got to do it right. And if anyone's ever done racks, you know that's not the easiest thing you can do. And so, you know, that was a harder part. Whereas Cassandra, it's kind of built in. This is what it's supposed to do from the beginning, based on this Dynamo background, Dynamo database. It's supposed to be spread out. It eliminates the single point of failure. Cross data center, again, relational databases have a harder time with that because you're going with something that requires this very stoic form of your data, and it's hard to get that data from one point to another. So when you talk cross data center, then you're talking about things like log shipping or, you know, some sort of complicated way to get the data moved over with some third-party product. I think Oracle has several of those. One of those is like something like Golden Gate, where that data has to get sent over and committed in a separate database. And if you get behind, then you're in trouble. With Cassandra, it was, again, built around the idea of spreading the data out, but spreading it out geographically. And again, with Dynamo, where Amazon was looking for, they wanted to make sure the data was all around the world. So that was the happy place for Cassandra. Linear scaling, again, relational database. Linear scaling meant a bigger box, right? So, hello, Dell? Yeah, I need that bigger one now. So that was how you scaled it. And if you wanted more, then you get into things like sharding, which then you're changing your application pretty horribly at that point anyway. So Cassandra, because you're spreading your data out in a way that works, is linear. And this is not, you know, this isn't just fanboy talk. This is what it was supposed to do. It's mathematically chosen to do this. And so it is doing it. You can go out and look at academic papers on how it works and proving that, of course, it is linear scaling, and it does work that way. But this is where I wasn't so happy. my original relationship with Cassandra was data modeling. And I was pounding my head. I went months just really trying to get my head around this. And there wasn't very much resources on data modeling. And I knew how to model relational data. And it just seemed so tough to think about it now in a complete, I can't do things. So I was very upset about that. So I'm trying to help. If you're in that position too, let's talk. So the data model, I get this a lot, and I understand. So NoSQL has always been pushed out as like schema-free, and it's kind of a free and happy database where there's nothing really constrained, and just go for it. And it's kind of like the 60s around your database, and not really. There are some that are like that, and there are some features that give you that ability. But think about it this way. You can't put data in a computer without having some structure. So yes, the data model, as I say, this is our kind of trolley headline here, but the data model is bad. Well, long live the data model, because you have to have a model. And so how does that work? So just like everything else where you model data, your data model is going to define those business requirements. So, hey, I'm building an application that stores things. Okay, what are those things? How do you want to store them? How do you want to retrieve them? And then the structure of data goes down to even like the types of data. I want to store ints, I want to store longs, I want to store text. So these are things that need to be kind of defined in the application process. And, I'll show you hopefully that Cassandra gives you those, all of that. It's different though, but it puts probably developers closer to what's happening in the database. And DBAs, if you're out there, you're getting closer to the application as well. But that's cool, because we need to work together. So the relational data model, which we've probably all learned well, is just one of a data model type. Go to Wikipedia, look up data model, and look at Wikipedia. They have a whole bunch of them. And network model, I saw that on there, and I'm like, I haven't seen that since 19, whatever. Well, if I had 19 in front of it. But there's just plenty of data models out there. It's just the relational is really kind of dominated for a long time. a lot of what the differences have to deal with are the two types of how we store data. And ACID and CAP, these are not data model, but they drive the data model. So relational databases are fundamentally all about ACID compliance, the atomic, consistency, isolation, and durability. I don't need to read the slide, you guys can read them. But this is really where relational databases sit, is in ACID. Now, boiling in ACID, no, that's a bad troll thing, can't say that. There are plenty of good reasons to have an ACID compliant database. And I'm not going to dispute that. But a lot later, when we start looking at what we're actually doing with our data, this is where the CAP theorem comes along. And back in the good old days when we all had 56K frame relay lines and no one was really pounding on our websites or grabbing apps, so we didn't have 1 million users on our page every second. ACID worked quite well. But when you look at the real requirements of the business, where you have uptime is really paramount and scaling is really paramount, and sometimes those just are really cross purposes with ACID compliance. So CAP theorem came along with this whole idea of consistency, availability, and partition. And you get to pick two of those. And it's not 100% pick two. It's not 0 on one and 100% on the other. But it's a trade-off. If you want maximum availability, you have to suffer a little bit either on partition tolerance or consistency. Now, what Cassandra does is it uses the consistency as the kind of flexible part of this. And that actually goes back to the Dynamo paper, where Cassandra's saying, look, you can tweak it. You want to make it 100% consistent, that's cool. But what you're going to sacrifice is your availability or partition tolerance in some way. But if you're not so worried about that, if you want maximum availability, then we can tune down the consistency. And the consistency will be more in line with your availability requirements and less in line with trying to keep everything 100% consistent. So tunable, that's good. As a programmer, I like to have options. I like features. I don't like to have these constraints. So a little background on relational databases. They're all built on this whole idea of these normal forms. This is the relational model, is that you have these little tables that store little parts of your data, and then you put them together. And so there are 5 normal forms, and if you can name them all, you get a big prize. I don't know what it is, but I got into like the 3rd or 4th one, and I was like, wow, no one uses those. But thinking about what you do with the relational model, here's the classic example. I think this is Scott Tiger database in Oracle. The employees and departments. So you have a list of employees, you have a list of departments, and then you do a join. So you have foreign keys, and the foreign key say, hey, these employees are related to this particular department. I'm going to join these together. And how you do that is you say, hey, I'm going to, oops, back up. I'm going to say, I want all the employees that belong to this certain department, and I'm going to join them together somehow. So there's there's more tables involved, but it's all about joins. And that's the key word here, joins. And that's going to be different. So the way Cassandra stores data is much different in that you're going to have your whole model built into this into a big type format. And so I mentioned before that Cassandra is built on McFadin when it comes to actually distributing your data, keeping it online, the partition type. But the data model itself is really big table. If you want to read the paper on big table, it's right there at the bottom. HBase uses big table as well. So if you use HBase, then this is very, very similar. The implementation is somewhat different, but really from a data model standpoint, it's very similar. The idea is that you have a row key and just a ton of columns. In Cassandra, it's up to 2 billion columns. So each row stores a dynamic range of columns. You can sort those, and the way that they're added can be dynamic. So this kind of data model lends itself to maybe not having any schema or having it completely dynamic, but it doesn't mean it has to be. And I'll show you why that's true. This is pretty important because the wide row is what I really stress on people when we talk about data modeling, because this is the power of the big table model. It scales really well this way. So the reason why is the way it's still. So the rows, I have my little cluster down here. Here's my 4-node cluster, and it's being replicated very nicely. The rows, each row belongs to a specific node and then is replicated across different nodes. But when that row key is stored on a specific node, it's also very randomized. So when I create one row key, it goes to one node, and another row key, it goes to another node. So I'm distributing my data, but it's replicating as well, and I can choose how well I want to replicate that data. So you can see how if you add more nodes, then it just spreads out the row key. That's going to make the linear scaling work really well. And if I want to replicate all 4 of these nodes to a different data center, it's just replicating per row key. It's not a log file or something like that, an incremental. It's going to be just the row key. So that fundamental atom of the row key with that huge amount of column space, that's where the data model, the Cassandra data model comes in, is that we want to use that row key. Row lookups are really fast. And then what we're getting out of that is a wide row, which is also very fast because it minimizes disk peaks. There's a lot more information on this, and if you want to look at some of my other webinars, I really dig into this, but I'm just going to cover the basics on this one. I don't want to dig too far into it. But this is important to know how to model data in Cassandra, just knowing what's going on underneath. So another concept we bring that we need to talk about from a relational is this whole idea of sequences. Now, I can't tell you how many times I've used them. I mean, every data model I think had at least a couple of them. And it's an auto ID or an auto increment or something like that. And they're just nice to have. And so whenever you create a table and it has an ID, which is an int or a long, and you just wanted to increment. Every time you add a record, you wanted to give it a new number, just one number. I put in a little, this is actually SQL, and I just want to, every time I insert this person, Ted Cod, in here, I want to grab whatever next value is. Now, that sequence I've created beforehand, that requires the sequence to be stored somewhere and have knowledge of it, but it also requires some blocking and some very idempotent operations. If two people ask for the same or next val, you want to make sure you do that in order, or two people, I would say, two programs ask for it. So it depends on making sure that you have this one very linear source of truth. You got to make sure that you don't have, I tried a long time ago to do distributed sequences, and it is so hard because you're spreading out this much information and you're going to run into collision problems, and that's a problem. But with sequences now, I'm mentioning this because this is one of the things I hear. It's like, oh, well, I used to use an auto ID or sequence. Well, how do I do that in Cassandra? Well, the short answer is you don't. But that's okay, because really what the sequence was trying to create was just some number that is unique. And that's fundamental that can be handled, but just in a different way. Because distributed systems, because all those sequences are going to be spread out all over the place, you don't want to have it so that you're worried about collision. So how do you do that? So there's a couple of ways to do it, and really I'd start with the first part, which is your data itself. Your data could have unique elements. Let's say that, going back to the business rules, you're storing user data. Well, the username, you want to make the username unique in your system. Okay, well, that's fine. Make that the row key, because that's probably what you're going to look up on anyway. The ID was really more important when you're doing joins, but we don't get to do joins. So that's part of the data that I have that I can create a row key with that I don't need to create an auto ID with. Now, in those cases where you don't want to use something unique in the data, but you want to guarantee uniqueness, UUID is your best friend. And you'll see this a lot once you get into Cassandra data modeling. And actually, most of distributed databases follow this same suit. UUID, universal unique ID. And I mean, when I'm talking universe, I'm talking about the entire universe. So it's a 128-bit number. Usually MD5 or something like that generates the number. But it's a 128-bit number that is created out of thin air. And usually there's some way to seed it or something. But the idea is that a 128-bit number is so vast. Yes, all right, math heads, all right, sit down. Yes, there's a potential it could collide. But I heard something very interesting about a 128-bit number the other day. I even tweeted it. It was, if a bit was a millimeter, and you had 2 to the 128 of those, it would be 10 trillion light years wide, which is wider than the known universe. So if you're feeling lucky, maybe you will get a collision. If you get a collision, go play the lottery, because you are that lucky. But that being said, just use UUID. So I don't think there's any programming language out there anymore that doesn't just generate UUIDs. Microsoft calls it a GUID because UUID is way too conformal. Same thing. If you look at it, it's the exact same thing. And you create this number and use it as your row key, and that is guaranteeing uniqueness. And very easy, handy thing to do. I put a little reference down there. It's RFC 4122, and you can go look it up if you want to get into the dirty details, but probably not. I bet nobody's going to go look at it. But got to put it on there, right? All right, so talk about what am I going to do with my data. So now we're actually getting into the Cassandra data model part. So we have a user table, which is entity modeling. And I think it's shocking. Some people think this is impossible, but it isn't. And this is a totally okay thing to do. Now, I'm using CQL, which is Cassandra Query Language. I'm using version 3, which is the latest and the one you should be using. If you're creating a project right now that will be released later, you should be using CQL. And if you're doing it in Java, you should be using our driver because it will make you a lot happier. That's the small plug I'll put in for it. But the language I'm going to be using, or the DDL I'm using, is CQL, Cassandra Query Language. It looks a lot like SQL because, yeah, let's face it, it's easier to transition from SQL to CQL. But the difference is going to be in what's actually going on in the storage engine. So let's talk about that. So this is my user table. And so going back to my uniqueness discussion, the username is the unique part. That's what I've chosen. Just like I said before, I'm not using UUID or anything, but the username I'm saying is unique in this. So I create this table, and it's pretty straightforward. I mean, we have typing, different typing, a lot of varchar one-time stuff. There's ints and longs. There's also a UUID type, which tells you how important that is to Cassandra. But this is a very simple table, just one primary key. And whenever I say primary key is username, what I'm actually saying is I want the row key to be the username. But I'm also just creating a fixed width table. This isn't going to be a infinitely growing wide row. This is just going to have just a few fields here, 6 fields. So that is what I would expect from the relational world. So it's similar to, to how you do alter table and relational. For Cassandra, a schema change is very lightweight. It's not a big deal. It's metadata. It's not actual data on the disk. So the metadata changes whenever you do an alter table. It's very low impact. It's not like you're going to have any maintenance time or downtime to deal with things. So it's very easy to change. But if you're doing a lot alter table inside your code, talk to me. I think we have better ways to do this, but it is doable. So that was a simple model. What happens when we get into these kind of things? Okay, here's my old friend, the employees and department table, and I have to do some denormalization. The denormalization was something I used to do a lot in relational databases, and mostly it was for performance because we have somebody creating a really complex join, and you do a select off of that, and it just turns into a long process, and you're like, well, wouldn't it be easier if we just put everything together? Well, let's talk about how that works. Like I said, very common concept in relational. So you're just combining things together. So like in this case right here where I have my employees and my department, and I'm saying, oh yeah, I want to make sure that employee ID number 1, I can join to Edgar Cott, and that's how I do it over here with my join. I have my select, and then from the department and employees, and I have my join on my primary key. And so, great, I'm going to be able to get that data if I use a join. It's a lot easier if I just said, hey, wait a minute, why don't I just put the department, because it's one-to-many, I'll just put the department inside the employee table. So this is denormalization. The normal forms in relational databases say you separate out that data. Denormalizing is unraveling that concept and just sticking everything in the same table. It's a lot faster if it's a single task and a single query, but it eliminates the joins, and that's what can really kill your performance. You can do a lot of other little tricks here, but this is basically what we're talking about when we say denormalization. So from a concept in relational, when I'm doing denormalization, completely translates into Cassandra world. And actually, this is the primary technique of taking a relational data and putting it into Cassandra, thinking about denormalization. So just like what I did before, so now I have my username, first name, last name, email, all combined together. Now I don't have to, I can put a department on there or something like that. But what about this? I have this relational, I have a relationship between my users and videos. Now, if you've ever seen any of my presentations before, I have my video database model, which I use quite frequently. If you've never seen one, in a nutshell, I have this concept of killervideo.com, which is a website to share videos. And users can upload videos, and then people can comment videos. It sounds a lot like YouTube, but it's better, I bet. Anyway, so it's all about just trying to find little things with modeling. And in this case, I have this one-to-many. I have any videos. And so how would I denormalize any of that? No foreign key here. So I've created two different tables. So what I'm actually doing here is I'm just going to store the information that I want in the video table anyway. Now, there's some lookups I can do, but hold on. So I'm just going to create a video table with this very simple setup, but I'm going to start putting data in there that I want. So if I'm just looking up videos, I'm just going to put username in there. I'm not going to do any joins. And so from an application, now think about this from the application standpoint. I'm writing an app. I have very specific things. Now, most times, anymore I talk to people, it's a web app or a mobile app. I don't know anybody that's doing anything but that anymore, and which is kind of a crazy thing to say because this is where we're at in 2013. But if you're watching this in the future, you may laugh. But web apps have state. You go from one page to the other. You're asking for one thing, and then you click, and then it sends a parameter, and then you go get it, and you come back to the next page. Mobile, same way. I need something, hit the button, it goes to get it, returns that nice JSON, puts it in your app. So it's all about this request-response cycle. Matching the request-response cycle in your data, in your model, makes a lot of sense. Hey, I want to look at this video. Click. Oh, here's all the information about the video, and including who uploaded it. Perfect. But what about this other situation where I want to look it up by username? Like, hey, how many videos did this user upload? And that's yet another question. Now, if you look what I did, I created another table for that. And that's okay because I'm modeling my data according to my application needs, but I'm creating multiple sets of data, which is really a byproduct of de-normalization. It's also totally cool because with Cassandra, you're going to get a lot better scaling anyway. Writes are cheap. Go for it. And whenever you duplicate data, yes, there is some cost in how much data you're storing, but I'll bet you're going to store less data overall just because of the way Cassandra allocates its data. But we're optimizing for one thing here. We're optimizing for the three first things. We're optimizing for uptime, for scaling, for lack of single point failure. So we're really trying to push that into the data model. So back to our good friend here, the username video index. So what I've done is I've created an index basically and into a column family. So when I want to look something up, now I've done something a little different here and I'll show you why. But I want to make sure that the username is the row key. So I want to say, hey, how many videos did C. Todd upload? Well, I want to look up by that person's name. I want to get all the videos. Or maybe I just want to get one video ID. I can grab that too. So think about it on a web page. I want to, when someone logs in, they just want to see all their latest videos that they uploaded in kind of a status bar or something like that. This would be perfect for that. Now, what I've done here with the primary key, pay attention class, this is important. The primary key, I have two things. I have a username and I have a video ID. What I've really done here is created a wide row. Going back to the original statement about big table modeling, I am adhering to that principle of big table, which is one row key, wide row. That's a happy place for Cassandra. So this is how I'm creating it. So what's actually happening here under the covers is when I say primary key, username, and video ID, I'm creating, the row key is going to be username. I'm using video ID to create what's called a composite column name, meaning that video ID will be attached to the upload date and video name as kind of prepended to each one, so that each time I upload a different video ID, I will get a different upload date and video name stored in a wide column, or in different columns in a wide row format. This is a big concept to get used to. Okay, chill. Okay, now I'm going to repeat that. The username is the row key. The video ID is the first part of the column name. The upload date will be the second part, and then it'll be video ID, video name for the second column name. And that makes it the video ID unique, but also you can store multiple video IDs in the same column or the same row with different column names. So This is how we're creating a wide row. Now, if you've used Cassandra before and you're trying to get into CQL, common myth I'm busting right now is that CQL does not do wide rows. Not true. Because what actually is happening, you're creating a wide row, but CQL is making it look like a table when you ask for it. That's all. So, enough of that. But this is how you would create an index to look for a username, and it's a de-normalization technique. So, another hard to get your head around concept is, all right, well, if I can't do joins, how am I going to do a many-to-many? And so concept of comments, it makes sense. You have users that can comment on many videos and videos that have many users commenting on them. So there's plenty of that. And then with a relational model, I'd usually use a joiner table. And the joiner table would create a join between users and videos, but also have some denormalization with a comment. And if I was really getting into my normal forms, the comments would be somewhere else as well. But we'll just, because this only fit on one slide, we're going to say we have 3 tables that need to be combined or used to combine to make we find out how many users commented on video or video what users commented on it. So the way I do that is, again, using a couple of Cassandra tables, I create the direction of which one I want to see. It's more or less like a materialized view. But what I'm doing is I'm modeling both sides. So I want to do comments by video and comments by user. And I'm changing it around so I can say, okay, I want to look up by the video ID. So consider this. If you're going to look at a video and I want to see all the comments that are underneath it, well, then you could do that. You could say, I want to just look up on the comments by video table by the video ID, select off of that, and then just give me an ordered row or an ordered output of all the comments. Oh, but wait, I logged in as a user. I want to go see all the comments that I've been making and see what's up. So I go over to my, as a user, now from an application standpoint, I want to look up by user and get a list of all the video IDs that that person has commented on. You are honoring the intent of a many-to-many, but you're doing it in a way that you don't have to do a join. You're denormalizing it into 2 separate tables. And this is completely legit. And why? Because you can bring on the writes. Cassandra does hundreds of thousands and millions of writes per second. It just is not a big problem. So if you have to write, if someone comments on a video, you should be very happy just doing a couple of those at the same time. You can do 2 different tables, 3 different tables, 4 different tables, 10, and that's fine. So you're optimizing. Denormalization, again, is optimizing for reads in the write cycle. That's a good thing to know. So the last big piece, transactions. Boy, if I had a nickel every time I heard that. Well, Cassandra can't do transactions. True, but let's talk about that. So what is a transaction from relational? So transactions have always been a part of, well, not always, but has been a very key part of relational databases. And they're just built in. This is what they do. I remember it was, part of our web performance and trying to get our applications, hey, do you have complex transactions? Because complex transactions lock things that may cause other strings or other threads to back up. So let's talk about, let's how we're going to minimize our transaction. So what we do is, in a nutshell, a transaction is you want to set a lock, you want to change table 1, 2, 3 in order, and then you do a commit on that. So you're really locking down this order, and you're also locking down the changes, so you don't have anyone else making changes during that time. Common example is bank accounts. I want to subtract from one table, plus on another, and then update another table with some other final balance, and then I want to do that commit. Well, or in the case where I want to change one table, I want to minus off the balance, add it to another account, update the final balance in another table. Oops, that errored out, roll it back. And that's got a lot of people happy, right? Because then they're like, well, if it didn't work, then you just roll back all the changes. It's like nothing happened. It's like a big eraser. And that could be very, very cool when that happens. And I understand that. I did that a long, long time. Problem is that these things can be pretty heavy, but when you need them, right? So what about that? So let's talk about Cassandra's point of view. I know, like, we'll just don't do it. Well, let's talk about that, because this is one of the things I found out in relational world before I found out in Cassandra world, which was when I would have a performance problem and somebody was doing a really complex transaction, I would have to ask them, are you doing that on purpose for a reason? I mean, is there a real reason for a transaction, or do you just want to update a bunch of tables? And most times the answer was, well, we're just doing it because we can. And we want to make sure, we don't want to have to manage any exception in our code. We just want the database to deal with it. All right, well, then you're not getting any scaling out of that. So here's a great article. I encourage everyone to go check it out. It is one thing that I ran across a long time ago that kind of changed my point of view on a lot of how transactions work. So the idea of this article, which I will give full credit to, was here's an asynchronous transaction, okay? I go into a coffee shop. Whenever I give the cashier my money, the whole line doesn't block until someone goes over and makes, let's say I get something really complicated, like a chai, mocha latte, something. So it's going to take somebody some time to make it. So I give the cashier my money, he puts in the order, we all just sit there and wait, the barista goes over and does it, brings it back, oh, that's not the right one, roll back, okay, go back and do it again, bring it back. Meanwhile, everyone behind me is like, dude, did you have to order the chai mocha latte? But that's not a way to run Starbucks. And if you've been to Starbucks, you know how they do it. You walk in, you say, I want a chai mocha latte or whatever, and they put it on a cup, they take your money, and then you step to the side. That cashier is done with you. And so you stand over in another line, and the barista comes over, here's your chai mocha latte with, like cinnamon on top. And I don't want cinnamon, I'll only do it again. So the barista takes care of the problem. And so it's a different domain. I don't go back to the cashier and say, roll back. If I did, I'd have a lot of people really kicked off at me at Starbucks, and they didn't have coffee yet, so they're probably on edge. So let's not do that. But that's kind of the point, is that you're putting the problem domain and the problem set into the application. So, and it makes sense. So if there's things that have to be managed, put them in the right spot, but don't block. Starbucks wants to make a lot of money. They want to have that cashier doing one thing, collecting money. You can deal with problems, handle the exceptions where they need to be handled. So that's my first part of this. Now, if you need transaction quality, it requires that lock. Like I said, that line's going to stop until you get your really complicated coffee, or moving on. So distributed systems, you can have servers all around the world. They're going to have a hard time with that. A distributed lock is a hard problem, but it's also one that's costly. It takes some time to do that. So Cassandra has features that give you probably a lot more assurance and give you a lot more of a better feeling about what you're doing. You're not just throwing data over the fence. So a really important one is row-level isolation. Row-level isolation is all about, if you update a row, if you're updating it, and someone comes along and reads it, they don't get half of the data that was there. Like if you're in the middle of doing an update, they don't get what you just updated and then the rest of the data. No, everything has to be updated, and then once it's done, it snaps that table over. And then, so as readers are coming along, as you're writing through it, they get a complete picture of the data. There's no inconsistent parts of the data. That means that you really want to make sure you maintain good data quality, use your row, which goes right along with what I was saying before. Row key, wide row, and that's going to give you good row level isolation. We also now in 1.2 have atomic batches. So I want this batch to run from start to finish in this order. So this is important for a lot of reasons, but also because you want to make sure when you throw a batch, because you can do a batch, it's not a transaction, it's not a commit rollback thing, but it's a batch. I want that batch to complete, or I want an error. So another way to handle this, which is something that I've seen in the wild quite a bit, and I have actually recommended and have used, is just keeping track of things going on. And this is something that Cassandra can do very well because it doesn't lose data. And it's very good about ingesting a lot of data, but it's also good at keeping data in order. And so it's all about tracking what happened, like a commit log. And you use the timestamps to preserve that order of when things happened. Banks, rectify your account based on how things happened. And if you think that banks are 100% acid, I've got a sad story for you. They're not. Banks use basically an eventual consistency type model with commits to make that work well. You can go to an ATM machine overseas, take out money like crazy. It's not like they're going to the bank and making sure that got committed and then they come back and say, okay, you got it. There's an eventual consistency to that. I've seen it happen. Not going to say who, not going to say where, but let's say I got some personal experience. You can overdraw your account by drawing money out of an ATM overseas. Because what happens is eventually those transactions make it to your bank and they're like, whoa, dude, got a little crazy there. Well, what does the bank do? They rectify it. They come and ask you. They say, you owe us some money, dude. So that following along that line, okay, how do we make this work for us? So I'm going to go with a credit. Okay, so I have an example here. So let's say, this video site, you want to put money on your account. So I create a credit transaction. So I'm going to use a username. The username does the transaction. And I have a flowchart of how to make this work. So a couple of key points about this particular column family is this credit transaction is going to be ordered by time. So username, and then the date time, and then the type of transaction. The date time and the type are the unique part of this, but think about how you want it to be. When I insert a new transaction, I want the latest thing to be the first thing on that row. This is not a FIFO buffer. I want to know what happened last time. So I'm going to reverse the order on that column, all of the columns on the row, so that whenever I ask that row key, hey, row key, what's your first item that you have? I want it to be the last thing that happens. And how I do that is I use this clustering order by syntax. So what I'm saying is I want the clustering order by, when you insert the data, it will sort the date time, it's a timestamp, in descending order. That's really a great feature because that means that in memory and on disk, it's completely sorted. You don't have to do any sort by or anything like that when you do the query. It's done. It makes a very fast read in that case. So that means I now have a transaction table. So as things are happening, like a commit log of things that are happening. So let's look at a complete, like how this would look. So, and I got these backwards. Ugh. So here's here's Ted Codd here, who's got his username. Here's all his transactions. Now, if you look at the timestamps on here, these are latest to in the past. So we'll start from the beginning. I need to rectify this account. So back here on 4/25 at 7 o'clock in the morning, he put in $100. Then at 3:45 in the afternoon, he took out $5. And then he added back $20 in 7 o'clock at night or 8 o'clock? 8 o'clock at night. So, or 9 o'clock, sorry. So what I'm going to do is I'm going to say, okay, now when I need to rectify, I'll just play it backwards. So I'll go to the last record and I'll play it back. So I'll say $100 minus 5 plus 20. Oh, you got $115 in your account. This is a very simplified example, but hopefully the concept is where I'm heading with concept. This is like an RPN calculator. You just start adding and subtracting and doing things, but when you get to the last thing, the one that's closest to the username, you should have a up-to-date balance. And if there's any question, you can replay all of it. This is event sourcing. This is what happens. So I'm going to go through the add a credit here as an example. So when I add credit, so I have this credit transaction record. So I'm going to put an add with a timestamp. And then I'm going to read from the user record. Let's say we're storing how many total credits they have, and they have a credit timestamp in there. So this is our user record, de-normalized. So I'm going to pull that out of the user record, and then I'm just going to do a quick comparison. is the user's credit timestamp less than the credit transaction on the timestamp? And if it is, that's a problem. If not, then what I'm going to do is I'm going to go ahead and set back to the user record. I'm going to increment it, and I'm going to add it to the credit timestamp, and then increment total credit. I'm sorry, I won't increment the timestamp. I'll put the timestamp of that transaction in the user record, and I'll increment the total credit and put that in the user record. Now, when I go look at the user table, and I say, how many credits do you have? Oh, you got $115 at the end of the day. That's correct. If there's any issue with that, I can replay the entire thing. And I can say, oh, this is what really happened. There is a problem here, or what have you. If anybody's looked at a bank statement, back in the day this happened a lot, not so much anymore, but it does, where your bank account is off. Okay, you got to go back to the bank and talk to them what happened. They have to replay all the stuff that's happened and find the error. Well, from an application standpoint, hopefully not so complicated, but you can see how you could do this. This is doable. And it's really pushing a lot of that to the application, I know, but let's not forget what you're getting out of this, which is now you can do this cross data center. Now you can do this without having to worry about scaling problems. Now you can do this without having downtime. So again, ask yourself, what am I trying to do with the transaction, and is this going to be sufficient? If it's not, if you need a full relational transaction, use a relational database. That's what I'm going to tell you. Because if you need it, use the polyglot persistence. And Cassandra can handle a lot of stuff, and the relational database can handle whatever it needs to. But I'll bet you if you start applying some of these methodologies, you'll find you won't need it very much. So finally, those of you who gotta have it, Cassandra 5026. That's, of course, since it's Cassandra development we're talking about, it's all in the Apache Jira, and Cassandra 5026 is the ticket number, the Jira number. Lightweight transactions are coming, and it's a way to do a distributed transaction, and it's pretty interesting stuff. It's coming in Cassandra 2.0, which is probably this summer-ish, but that is going to satisfy a lot of those requirements, I think, and just stay tuned. That was that, but that's not all. This was a kind of basic run-through, but we're going to go a lot farther. So if you liked what you saw here, you want to know more, May 16th. Become a supermodeler. I am going to do another one of these, which is kind of leaving where this left off and just taking it into a whole new dimension. And we'll talk about advanced indexing, some of the more complicated data models, but really it's going to be a progression. And then finally, I'm going to do my last one, the world's next top data model, which, no, I'm not going to have real models on stage, but that'd be cool. But it'll be at the Cassandra Center, and that's on June 11th. It'll be an hour talk. You get to see my shiny face. I'll be up there. But that's going to be the third part of this series. And I really encourage you to be there and show up and do this. It'll be in a huge room, Fort Mason, in front of this big bridge thing. What is this? Golden Gate. The Cassandra Summit, if you're on this webinar because you want to know more about Cassandra, if you really want to know more about Cassandra, be at the summit. We have world experts. We have people doing stuff that you want to do, probably. I mean, look at the lineup. I'm just put a few. Sony, eBay, Netflix, Intuit, Spotify. These are real companies doing real things, a lot of real things with Cassandra. And if you think your problem is unique, bring it and let's talk about it. I'll be hosting an expert session there too. So get in there, sign up. I think Paige put up a discount code. Use that. But come and meet me. I'd love to talk to you about what you have going on. And I think we're in the question and answer section now.
Great. Thank you so much, Patrick. So if anyone has any questions, please submit them through the Q&A box. We've had a few come up since you started. First one, given the users table example, how would you ensure uniqueness of username?
That's a good question. And in that case, you still have to do a read before you do a write. And that, I know that's kind of an anti-pattern for a lot of places, but you still have to do a read before you do a write. Now, the lightweight transactions that I mentioned in 5026 actually is about that problem right there. I don't want to have to do a read before a write. I want to do a conditional check and set. And so that's what's coming in Cassandra 2.0 is the elimination of that read before a write, which I agree is not the best way to do it, but that's how you manage it.
Okay, great. Next question. Does Hector support atomic batches?
Hector does not. Hector is using thrift. But actually, no, let me take that back. It will if you do a batch. But in Cassandra 1.2, it's actually managed from the node level. So it should be able to manage it. I'm not quite sure about the exception support. If you're going to go down that direction and you're using CQL and you want to use newer features, I really would encourage you to look at our Java driver, DataStax Java driver. It's really the future direction of where Java development for Cassandra is. It would probably be in general release next week. But I would encourage anyone who's doing Java development right now and C# development to look at our drivers because they're a completely different way to do it and they're really nice, really nice.
Great. Next question. Cassandra 5026 is the already fixed reduce log spam from counter shard warnings. What is the right ticket for the lightweight transaction?
Oh no, did I get it fat fingered? Oh no, I got called out. I better change that too. Hold on. You know, there's a lot of tickets in there. I'll look it up.
All right.
Yeah.
We'll get back to that person, or can you answer right now?
No, I'm looking it up right now.
Okay.
Go ahead. Well, get the next question while I'm looking it up.
Okay, next question. I guess someone missed this part when you were talking about Java. What did you mention that we should use if using Java?
That's the Java driver. I mean, I think if you're doing new development now, new projects coming out soon, like the next few months or later, you should really be using our Java driver. Askianix and Hector are using the thrift transport, and our driver is using CQL binary. And so if you're using CQL3 and the examples that I put up, you'll want to use our driver.
Okay. Next question. This is on composite columns. Are there any columns that are common to all of the composites, a field that can be updated across all of the composites?
That are common to all composites. Let me think about this. Read that question again.
Are there any columns that are quote-unquote common to all of the composites, a field that can be updated across all of the composites?
Oh. Right. Okay. The answer is no. However, you might want to look at, and this is my next talk, but I'll be talking about collections. You can also do collections now with Cassandra. So that might answer that better. That will be in my next webinar, though. A little more complicated example. But when you use composites, when you have a second key in your primary key, it will be attached to all. You can only have that one set in that one row. So it's going to have that part of that primary key in every column.
Okay. Next question. How difficult would it be to, let's see, initiate a Cassandra instance for another Cassandra instance? Would that be possible? Do I need to rely on backup and restore procedures?
Well, How difficult it is to do what? Say that again. By the way, 5062. I got it backwards. Okay, so say that again. I'm sorry.
How difficult would it be to initiate a Cassandra instance for another Cassandra instance?
To instantiate. Not quite sure if I got the question. What's the intent of the question?
If if Marcos, if you could maybe rephrase your question, we can go ahead and ask it again. Looks like we have time for maybe 2 more quick questions. Is there a size limit on the image or text data type?
All right, so the column names have a 64K limit, but the column values have 2 GB limit. So yes, there's a limit, but it's one of those limits that don't even go near it. It's a lot of data to be setting into your database in the first place. If you need to do that much data in one column, I would probably point you at some ways that, say, like Astyanics does. It breaks it into blocks. It's just not as efficient to just stream gigabytes of data across to one column. If you break it into pieces, then you wind up spreading it around your ring a little better. There's some ways to do like block storage. That's how we do, for instance, our Cassandra file system. Instead of storing one big blob of information in one column, we break it into chunks, like 64K chunks, and we spread it around in different column families, or I'm sorry, in different rows. So yeah, those are the limits, but you know, based on what you're probably trying to do, there's probably some better ways to do it, more efficient.
Okay, thank you, Patrick. It looks like we're a little past the top of the hour. Thank you so much for presenting, and everyone, thank you for joining. Again, if you are interested in learning more about Cassandra, please sign up to be a part of our Cassandra Summit, June 11th to 12th. There's an early or a discounted ticket code SFSummit25. You can get 25% off of our regular ticket prices. And we will host the second part of this 3-part series May 16th at 11 a.m. Pacific Standard Time. So thank you so much, Patrick.
All right.
All right.